let us just begin after a few minutes and wait to see if somebody else is willing to join. Yeah, good evening, everyone. Uh, am I audible and is the screen visible to everybody?
Yes, sir.
Okay. So I welcome all of you to the 11th live session of the course Fundamentals of Manufacturing Processes, which is being offered by Professor D.K. Divedi of IIT Roorkee. And as in for myself, I am a Big Dev, a PhD scholar in the Department of Mechanical Engineering at IIT Bangalore. So today we shall be discussing on the concepts related to the welding of the metals, um, welding of materials, and uh, also an introduction to the different kinds of surface modification techniques. So without further delay, let us begin today's session. So the first will be a numerical related to the butt welding process. Uh, the question is, two 6 mm thick steel plates placed 2 mm apart are butt welded at 6 mm per second using 30 volt, having heat transfer efficiency of 80%. The heat required to melt the steel is 12 joule per millimeter cube and the melting efficiency is 80%. Determine the welding current required. Okay, so what is the process here happening? There are two plates, thick 6 mm thick steel plates. Okay, so the thickness of the plates are 6 mm each. Okay, and they are placed 2 mm apart. That is this thickness, or yeah, this is 2 mm. Now they are butt welded at 6 mm per second. So supposedly this is the welding torch, a simplified say a schematic of the welding torch, and the material and heat are both deposited, are both coming from this. So this is welding the joint. This is here to pour the material into the joint, and this moves at a speed of 6 mm per second in this direction. The so the current, the voltage that is supplied to the there is some particular voltage and current that is for power. Some voltage and current will have to be supplied so that the melting takes place. So the voltage here is 30 volt, and the current to be supplied is to be found out. This heat, the voltage and current, they are supplied at a heat transfer efficiency of 80%, and the heat required to melt the steel is 12 joules per millimeter cube. So for melting 1 millimeter cube of the steel, the heat required is 12 joule. Okay, and the melting efficiency is 80%. Okay, so like although 12 joule per millimeter cube is required for the melting, but more heat is to be supplied because the melting efficiency is 80%. That is, if we are supplying mm, say 12 joule, only say mm, 9.6, it will be 80% of that will be used for melting. That is the uh, meaning of having a melting efficiency of 80%. So this is the melting efficiency, that is if 12 joule is supplied, okay, only 9.6 joule will be used for melting. Since 12 joule itself is required for melting, so we need to supply more than 12 joule. That is mm, what I can say, So more than 12 joule needs to be supplied for the melting of 1 millimeter cube. We will find out the details, and what is the significance of the heating efficiency. The heat transfer efficiency is that, suppose from the welding torch we are supplying say 100 joule of energy. Okay, then only 80 joule of energy will be reaching the base metal, and the remaining will be say lost to the heat, or will be transmitted through the welding torch itself, and the remaining will be lost to the lost as heat to the ambient. So 80 joule comes to the base plate. Now this is the melting efficiency or heat transfer efficiency, sorry. And this 80 joule will not actually be taking part in the melting operation. So 80% of these, that is only 64 joule, will be taking part in the melting of the base metal. That is the melting efficiency melting. Okay, so this is what is the um, uh, you know uh, taking in account of the losses of the heat energy during the transfer of energy from the welding torch till the till ultimately there is melting of the base metal. Okay, so the melting efficiency is 80%. Okay, now so how to proceed with this? We have to first determine what is the area of the weld being uh, made in this. So when this is the area of the weld that is that will be uh, propagated with the speed of 6 millimeter per second. This area of the weld multiplied by this velocity 6 millimeter per second will give the volume uh, of the weld produced per second. Okay, so what is the area of the weld? That is 6 multiplied by 2 millimeter square, that is 12 millimeter square. Now the volume flow rate or the volume of the weld produced per second, weld to be produced per second, that is volume of the weld, say volume of the weld, rate of it is given by area of the weld multiplied by this velocity of welding, that is 12 multiplied by 6 millimeter cube per second. So this is 72 millimeter cube per second. So the material to be melted is the rate at which the material to be melted is this. Therefore rate of melting of material is equal to 72 millimeter cube per second. Now so energy is to be supplied at this rate such that 72 millimeter cube of material is melted per second. Okay, so the energy is to be supplied in such a way, in such amount or rate, such that 72 millimeter cube of base metal is produ is melted per second. Since 12 joule is required for melting 1 millimeter cube, so energy required for melting will be required for melting per second is equal to this 12 joule is required for melting 1 millimeter cube of the material multiplied by, we take this, what is melted per second, 72 millimeter cube is melted in 1 second, and there will be melting efficiency, sorry, why 1 upon the melting efficiency, that is uh, uh, 12 joule, a fraction, an amount more than the 12 joule will be required for melting per mm cube, else we can find this one as um, actual energy required for melting 1 millimeter cube is 12 joule divided by this melting efficiency. Okay, that is why we multiply this with the amount of material to be melted per second to give the energy required per second to be supplied. So this value comes out to be or just a minute, we can find this one first. Since this is the energy, actual energy required for melting 1 mm cube, this is 12 by the melting efficiency joule, that is 12 by 0.8, that is 15 joule. So for melting 1 millimeter cube, 15 joule of energy is required. So here we can put 15 joule per mm cube multiplied by 72 mm cube per second. So this is 1080 joule per second. So this is the energy to be supplied per second. That is, this is the energy that is to reach the base metal, not the energy to be supplied. Okay. Therefore, energy to be supplied will be equal to 1080 divided by the heating efficiency. So this will account for the losses that will occur due to the transfer, during the transfer of heat from the welding head till the base metal. Okay, so the amount of heat to be supplied by the welding head is equal to 1080 by the heating efficiency. So this will be 1350. Therefore, the current to be supplied I, this is equal to energy to be supplied by the voltage, because power, this is power basically, right? So power is the voltage multiplied by the current. So we are just dividing the energy by the voltage to get the current to be supplied. So this is 45 ampere, which is option number A. So the correct option is option number A. So is it clear to everybody? If there is any doubt, you can ask.
Yes, sir, clear.
Okay. Then let us move on to the next problem. As energy density decreases for welding of a given base metal, the heat affected zone, it decreases, increases, remains unaffected, or it increases and then decreases. So any idea about this? Can anybody give me the answer to this? Okay, see, what happens is, for melting, for welding, we need to melt the base metal, right? For welding slash melting of a given base metal, a total fixed amount of energy per unit volume of the metal is required. That we saw, like in the previous problem, it was 12 joule per millimeter cube. So whatever be the energy density, 12 joule per millimeter cube, for every millimeter cube of the material to be melted, 12 joule must be supplied. Okay. So this is a fixed amount of the energy required per unit volume. Okay. So as energy density decreases, so what is energy density? Suppose 10 joule was initially supplied to 1 millimeter cube. Okay, the energy density will be 10 joule per millimeter cube. Okay, now if the 10 joule is supplied to 0.5 millimeter cube, then the energy density will be 20 joule per millimeter cube. So as the energy, this is the increasing energy density, and if the energy density decreases, say if now 10 joule is supplied to 2 millimeter cube, then the energy density will be 5 joule per millimeter cube. So greater the area being affected. Okay, so this is the area being affected because of the heat, that is 10 joule is supplied to a greater area here, a medium area here, and a very smaller area here. So greater the area onto which a particular value of energy is supplied, the lesser will be the energy density. That is, as energy density decreases, we can consider that a fixed volume of energy is now affecting a greater area. But since for melting a particular base metal, a fixed value of energy density, energy is required for melting 1 millimeter cube. Say that energy is 10 joule per millimeter cube, then at this energy it will melt directly, like it will melt that area, this area will be melted. But since it is 5 joule per millimeter cube, okay, so the energy to be supplied, that is, you will have to supply this energy. So say this melting would have happened in 1 second only, but here the melting since it is affecting a bigger area and the energy density is less, so to supply 10 joule of energy for 1 millimeter cube, the time required for heating will also be more. The time required for heating will be more for this case, since it has to give ultimately 10 joule of energy. So supposedly the power that we are giving is say 10 watt, or in this case it is mm, say the power that we are giving here is 5 watt here, okay, and it is 10 watt here. So you will have to give 2 seconds of this power to reach to actually give 10 joule of energy to this 1 millimeter cube of area for this to melt, okay. So what we will see is that during this time, that the time of heat transfer will also be more, also the area of the heat transfer will also be more. Since the area of heat transfer is more, so actually we would have required to melt only this much of area, but since the area on which the heat is interacting is more, so a greater value of region will come under the heat affected zone, okay. So this entire region will result in a greater heat affected zone, and here the heat affected zone say will be like this, here it will be further smaller. So as the power density or the energy density decreases, the heat affected zone will be larger and larger. Say we you can consider this, we are concentrating the heat source onto a very small area, then the energy density in that location will be very high, it will melt faster for a given base metal. If we are using now a larger area, it will be the energy density will decrease, the same heat if the same heat is supplied, then the energy density will decrease. So to melt the area, more heat or more time, sorry, to melt the same area more time will be required. Also, since it is interacting with a larger area, so the heat affected zone will also be larger in this case, okay. So as energy density decreases, we can say that the energy supplied interacts. This can be one case, or alternatively there can be another case wherein say we consider that 2 millimeter cube was the area that was being heated in this case. Another case can be where say 1 millimeter cube is only heated, but the energy supplied is 5 joule, okay. That will also result in a heat energy density of 5 joule per millimeter cube, which will be less than what is required, that is 10 joule per millimeter cube. So energy density can be that the actual power that we are supplying is also less, or the area has increased. So it means that the either the energy supplied has decreased, or the area on which it was acting will increase. In both the cases, if 5 joule we are supplying now, then also we will have to supply for a longer period of time to supply the 10 joule to this 1 millimeter cube, so that the melting happens. If the area is widened, then also it will interact with a larger area, and as such the heat affected zone in both these cases will be more, okay. So as energy density decreases, energy supply decreases, or area of interaction increases, okay. This results in a larger heat affected zone. So as the energy density decreases, the heat affected zone increases. Okay, so is it clear to everybody?
Yes, sir.
Okay, then let us move on to the next problem. So epitaxial solidification occurs when no filler material is added. Filler material of different composition is added. There is no melting of the base metal, or the base and filler material are soluble in each other. Yeah. So uh, so can you give me the answer to this, or if you don't know the answer exactly, can you just begin with what is epitaxial solidification? Yes. So what is epitaxial solidification?
No, sir, don't know.
Okay. So so epitaxial solidification refers to the solidification when there is no uh, uh, nucleation or no new grain formation, only there will be grain growth. Okay, so say this is the base metal which is melted. Okay, this is base metal. Okay, and there are when this has melted, there are the grains in the base metal were in this structure. That is, some of those have already melted out, and the remaining. So this is the melt zone. This is the melt zone. Now, if the filler material added, if no filler material is added, then the base metal only will be filling this melt zone also. If the filler material is same as the base material, then also material of the same composition as the base metal will be filling this melt zone. Okay, if no filler material is added, or the filler material is same as the base material, then mm, the melt zone is filled with molten material having same chemical composition as base metal. Okay, now you see, if the if so since it is the same chemical composition, so you can see, suppose you consider that these grains have been cut or wounded. Now since the molten layer here is the same as this composition, so this, from this cut or wounded regions only the grains will start growing, that is the grains will start becoming complete like this. Okay, new grains will not form at the boundary. Okay, only the grains, that is there will be no nucleation, there will be only growth of grains. Okay, there will be only growth of grains. There is no nucleation, only growth of grains. This is called epitaxial solidification. So this is possible only when in the melt zone the chemical composition of the molten material is same as the base material. Because if the chemical composition is different, then that chemical different chemical composition, suppose the base metal was of iron. Now if here in the molten region iron and say nickel both are present, then nickel will start to form different grains and iron will start to form different grains. As a result, this kind of formation of grains, this kind of growth of the grains from the existing grains at the boundary of the melt zone will not be possible. So epitaxial solidification is possible only when this is happening. So only possible when this is happening. Okay, so the correct option will be either no filler material is added or the base material or and the filler material are same, having same chemical composition. Okay, so the correct option is option number A. Along with it, no filler material is added. If this was mentioned that filler material is having the same composition as a base metal, then that would also be correct. Okay, so is it clear to you?
Yes, sir.
Okay, so the next problem, electrode wire is laced in which of these? Direct current, reverse polarity, direct current, straight polarity, alternating current, or it does not depend on the current, only depends on the electrode material. So concepts like this we have already discussed, so I think you should be able to answer this. uh, think in the direction in which of these the maximum heat will be generated in the electrode. Yes, so first tell me, like, will it depend on the current or not? We already discussed some of these, right, in the when we talked about the polarity and in which case more heat will be generated in the workpiece and more heat will be generated in the electrode. So like if the electrode wire will depend on the current or not. Yes. See, if you don't interact, it will be very difficult to understand if you are understanding or not. Yeah. so, you are saying that the electrode wear will not depend on the current.
No, sir, I am saying that I don't know the answer.
Okay. So see, electrode wear, we have seen that there is something called positive polarity, there is something called negative polarity. Okay. So if the electrode is positive and the workpiece is negative, that is called a direct current reverse polarity. In direct current straight polarity, the electrode is negative and the workpiece is positive. Then this is direct current straight polarity. What happens in alternating current? The polarity of this keeps on changing. It will be plus and minus, and this is minus and plus. Okay. So like for 50% of the time, it will be reverse polarity, and 50% of the time it will be straight polarity. So obviously the electrode wear depends on the current. So that is obviously depending on uh, um, how the current or what phase the current is supplied. So this option number D will not be correct. Now in alternating current, straight polarity and reverse polarity of direct current, so we have to see that in this case, since electron will be moving from this to this, two-thirds of the heat will be generated in the electrode, and one-third of the heat will be generated in the workpiece. Here one-third of the heat will be mm, generated in the electrode, and two-thirds of the heat will be generated in the workpiece. Here it will be, since it is reversing, so for some time it will be two-thirds on the electrode and one-third on the workpiece, and for other 50% of the time it will be one-third in the electrode and one-third on the workpiece. So sorry, two-thirds on the workpiece. So it can be said that half and half of the heat will be generated in this case over the entire cycle. Okay. Now, the more the heat generated, the more will be the wear, right? So, since more heat is generated here more heat is generated, maximum heat generated at electrode. So, more heat implies more wear of electrode. Okay. So, the electrode wear will be maximum in case of direct current reverse polarity. So, electrode wear is maximum for direct current reverse polarity. Okay. Now before concluding, I would like to ask you if you know how this two-third and one-third heat is being generated at electrode and cathode, electrode and the workpiece. Do you know that?
No, sir.
See, how the heat is generated depends on the electrons. See, if the electrons are moving from the electrode to the workpiece, then when the electron strikes, the electron will have a particular potential energy, for particular kinetic energy under this potential field. In this potential field, since it is being attracted towards a positive terminal, what happens is that um, the electrode will get accelerated towards this positive part, and they will have develop a kinetic energy. When this electrode, this kinetic energy, when the electron strike this material, this kinetic energy will get transferred to uh, heat, the thermal energy, which will be required for melting the material. Okay. So more the electrons are moving, and more will be the generation of heat in that case. Here the electrons are moving from the workpiece to the electrode, so more heat will be generated in the electrode. The reverse of what happens is that under this case, when electrons are moving, you can say that the some positive charges are attracted, positive charges, or you can, if these were semiconductors, we would have considered holes, but here let us consider some positive charges which are moving towards a negatively charged. So this will be lesser as compared to the electrons that are coming due to the positive field. So and these positive charges will not be uh, you know significantly, since they are these charged particles, when they even if some charges are actually being transferred, or you can consider that the here there was actually an excess of electron on the negative side. Now this excess of electron is being filled up by this due to the um, transfer of electron out of this negative electrode. The excess of negative charge is being filled up gradually by a equivalent positive charge. Okay, so the resulting heat generated because of the transfer of electron from this, okay, will be one third of the heat. And the because since the main kinetic energy, the action of the kinetic energy of the electrons is coming on the positive terminal, so the two-third or 66% of the heat will be generated in the positive terminal. So depending on which one is a positive or which one is a negative terminal, more heat will be generated in the positive terminal and less heat will be generated in the negative terminal. So have you understood now?
Yes, sir.
Okay. Coming. Yeah. So have you understood properly, like why more heat is being generated in one case and less heat in the other?
Yes, sir.
Okay. So so now is it clear how the electrode wear will be maximum for reverse polarity?
Yes, sir.
Okay. So coming to the next problem, in gas welding, the inner flame temperature in degrees Celsius is around which of these? So I want all of you to think about the gas welding process and the inner flame temperature and give me and type the answer. I will just be back in 2 minutes.
Sir, 3000.
Okay, so let everybody answer, and I request all of you to type the answer in the chat box, and mm, and those who are done with that can think about this. In gas welding, inclusion is less because of which of these? So think about this and give the answer to this too, and I will be back in 2 minutes. Yeah, sorry about that. So, could you give the answer to this? The answer to this, in gas welding, the inner flame temperature in degree Celsius is around which of these?
Sir, 3000.
Okay. Uh, I was expecting, I had asked everybody to write down the answer, but I think people are not very much are not feeling very much interested to give answers. Anyway, so in gas welding, what happens is uh, there are regions like this. Okay, so the inner flame temperature is around 3100 degrees Celsius, and the outer temperature is around 1275 degrees Celsius. So, why these two regions are having different temperature? Can you tell me? Because these two are formed from two different reactions. That is why two different they are resulting in different temperatures. So in gas welding, what happens? This is ethylene, or sorry, this is acetylene, and this is when there is a burning of acetylene with oxygen, it results in an like an exothermic reaction, forming carbon monoxide and hydrogen, and there is around 18.75 megajoule of energy. Okay. Now, this is the amount of energy produced in this. Now, this is responsible for the outer flame temperature. What happens is that this carbon monoxide will undergo further reaction with it. So, 4 carbon monoxide, this is responsible for this reaction. Okay, and 4 carbon monoxide and 2 of hydrogen hmm, reacts with 3 oxygen to give 4 CO2 plus twice of H2O. Okay, plus this results in around 35.7 megajoule of energy per meter cube. So this very large release of heat in this exothermic reaction is responsible for this inner flame temperature. Okay, so that is why we get two different flame temperatures in gas welding. One is of around 3000 degrees Celsius and one is around 1200 or 1300 degrees Celsius. One, the outer flame is by the burning of acetylene directly, and the other, the inner temperature, is because of the oxidation or of carbon monoxide and hydrogen gas to form carbon dioxide and water, releasing an enormous amount of energy. Okay, so the inner flame temperature is around 3000 degrees Celsius. Okay, so is it clear to you?
Yes, sir.
And I request everybody to please be interactive. Otherwise, like, I am not able to understand if you are where you need clarification and on which aspects you need clarification. So only this will be clear only when you people are more and more interactive. Anyway, so in gas welding, inclusion is less because of which of these?
Sir, I think option A.
Okay, why? Like gas welding, why will there be a less interaction?
I think so, sir. D.
Yes. So yeah, the correct option is option number B. The impurities float over the surface. Okay, why does this happen? Because you see, heat the gas welding is not very much focused like laser welding or electron beam welding. So it the energy density will be less, and since the energy density is less, it will have to heat a larger area of the material for the melting to happen. Okay, so the heat effective zone increases, and also because the substrate is getting heated to a larger section, so the cooling rate in this case will also be lower. For a lower vessel, it is solidifying slowly, so the impurities will get the time to start floating on the surface. If it is very fast, then the impurities do not get a time to start floating on the surface. See, supposedly if you take a bowl of water and you place some impurities on it, initially the impurities will be you know it will be dipped completely in the water, but once you let the water rest, then the impurities will start to get collected at the top. Okay, or if it is very heavy, then at the bottom. But for lighter impurities, mostly inclusions are happening mainly because of the lighter impurities, which will then start getting uh, or which will start floating on the surface of the melt pool. That is why the inclusions inside will be less. That is, the inclusions due to these impurities will be lowered, because these impurities are mostly will now be on the surface. Okay, so inclusions are less because impurities float on surface in gas welding. This won't be possible in case of laser welding or electron beam welding, because the cooling rate is extremely fast. It is actually, the cooling rate is in the order of 10 to the power 4 to 10 to the power 6 kelvins per second. Okay, so in that case, the solidification will happen instantaneously before the impurities, any impurities if present, have the time to come up to the surface. Okay, so that is why in gas welding, impurities will have the time to start floating on the surface, and that is why the inclusions will be less. Okay, now the cleanest joint is formed in which of these? Gas tungsten arc welding, submerged arc welding, shielded metal arc welding, or gas welding?
Sir, option A.
Yes, gas tungsten arc welding. It will have the minimum amount of oxygen and nitrogen in a weld pool, because an inert gas, say argon or something, will be used to cover the weld pool or make an inert atmosphere, so that minimum amount of oxygen and nitrogen can get into the pool. That is why the cleanest joint is obtained in case of gas tungsten arc welding. In gas tungsten arc welding. Okay. Now, the next problem, as energy density increases, the thermal damage to the workpiece increases. Well, like as energy density increases, what is the effect on like what will be the effect on the thermal damage to the workpiece and the penetration on the workpiece? So can anybody give me the answer to this?
Sir, I think decreases. Both will be decreases.
Okay. Okay, so you are saying that as energy density increases, the penetration on the workpiece decreases. So, we have already seen, like, see, consider this as a force. or energy that is coming, not force, energy, it is interacting this one. So a higher energy density will cause a penetration like this, or a lower energy density will cause a penetration like this. What I am trying to say is, let me reframe it. Suppose this is the energy density of 10 joule per millimeter cube. So it will, with this amount of energy, the penetration, the melting to the depth will be more, or suppose this is the energy density of 5 joule per millimeter cube. In this case, the penetration will be more. That is, the melting to the depth will be more. In which of these? Consider these as forces. Okay, here 10, suppose 10 value of force is coming, so the impact will be felt to a greater depth, or here 5 joule is 5 value of force is coming, the impact will be felt to a greater depth. Or rather, you think it in this way. This is suppose 10 joule, 10 joule per millimeter cube. This is 10 joule is coming from this side, okay, and one is 10 joule per 2 millimeter cube. So 10 joule is coming from this side. So but this 10 joule can suppose melt only 1 millimeter cube of the material. Then in this case, the 1 millimeter will be like this, or in how will be the 1 millimeter in this? Won't it be like this? If this area is 1 millimeter cube, then since the width in this case is less, so the depth for 1 millimeter cube has to be more, so that this energy can melt up to that 1 millimeter cube. Whatever the increase in the depth, in whatever increase in the width from here to here, is compensated by, should not it be compensated by the decrease in the depth? Like, if you are understanding this, please say so, otherwise I will not be able to understand where you are not understanding. Okay, let me put it this way. Suppose I have 100 rupees here. This I am giving to two people. Okay, and if we place whatever amount they each person has, then what amount will each person have here? 50 rupees, right?
50-50. Yes.
Now I have 100, same 100 rupees. Okay, I am now giving it to 10 people. Okay, now what will be the share per person?
10 rupees.
Yeah, so now you considered it uh, as the depth like this. So yeah, 100 rupees, two people is 50. 100 rupees, sorry, 10 people will be 10. So in which case will be the penetration more? In which case the money is more? You tell me. In which case is the money more per person?
In first one.
Yes. So similarly, in this case, take this as the energy. Take this as the energy. Take this as the area. Okay. This is energy and this is area. Then the penetration or the effect per per length of the direct per along the length, the effect will be felt more in which case?
In where in a small area.
Yes, where the area is small. So where the energy density is higher, the effect will be more in the in along the length direction, that is the penetration. Along the penetration, the area will be more, sorry, the effect will be more. But see, if we take the heat affected zone, which one has the more heat affected zone?
In case 2.
Yes. So now is it clear, like previously we were saying that for energy
Yes, sir.
decrease in the energy density, the heat affected zone will be more. So how the heat affected zone is affecting the the heat affected zone is being affected by energy density, you understood now?
Yes, sir.
Okay. So now we can say that as energy density increases, okay, the heat affected zone will decreases. Since the thermal damage is a measure of how long till what zone the effect of the heat transfer has happened. So with decrease in heat affected zone, the thermal damage, since the heat affected zone is decreasing, that means the thermal damage is also decreasing. Also the penetration, as we have already seen, the penetration increases. So the correct option is the thermal damage to
D.
the workpiece decreases and the penetration on the workpiece increases. So actually, if you plot this curve, if you see here, if this is the thermal damage and this is energy density, then the thermal damage will decrease like this. And towards this section, the you will get better, higher penetration. And since there is higher penetration and lesser thermal damage, so the surface finish will also be higher in this region. Okay, so is it clear to
Yes,
you?
sir.
Yes. Yes, sir. Yes, sir. Very much clear, sir.
Okay, so coming to the next problem, liquidation cracking in fusion welding process generally occurs at which of these? Liquidation cracking in fusion welding process generally occurs at which of these? Yes, so any idea about this? See, there are two different types of cracking that we mainly consider during a weld. Suppose this is the melt pool and this is the heat affected zone. Okay, so in melting from this region, uh, the solidification has happened. So during solidification, if there is improper thermal expansion and contraction, then there will be cracks in this, that will call cracks here during at the from the center of the melt pool. This is called the solidification cracking. Now this is solidification cracking. And in the heat affected zone, what happens is that there are, because of the increase in the temperature, there will be expansion, okay. But when the temperature decreases, like the material will again try to contract back. During this process, if since the heat affected zone will now be surrounded from both the sides, one from the melt zone which is solidified and another from the base material. So during this expansion and contraction, due to this thermal stresses, hmm, thermal stresses near the boundary of the melt pool, this thermal stresses can result in cracking, which will be called liquefaction cracking. Okay. So from the, this happens from near fusion boundary. Okay. So the correct option is option number B. Okay. Is it clear to you?
Yes, sir.
Okay. Now this one. So hypereutectic steels, as per the FEC diagram, contains, that is iron carbon diagram, contains the phases of which of these? Hypereutectoid steels. Yes, any idea?
Option C.
Yes, option C is correct. So, um, in hypereutectoid steels, can you tell me what will be the fraction of carbon in it?
Sir, 1.7%.
Is it 1.7%? Think about it.
Above 1.7%.
It is not 1.7%, it is above 0.8%. Not 1.7, okay. It is above 0.8%. So, you see, if we mm, draw the diagram, so just a rough diagram I am drawing, because you will find this in most of the textbooks. And this is the carbon content, okay, percentage carbon content. So the first we reach this point, this is very low, 0.075%. Then we have this point, okay, above which is the eutectoid point. This is 0.8%, and this is the eutectoid point, okay. This is the gamma region. Here this is gamma plus alpha, this is alpha, this is alpha plus perlite region, this is gamma plus uh, cementite region, and this is perlite plus cementite region. What is perlite? Can you tell me what is perlite? What is perlite? Perlite is
where only the layer is going to deposit.
only what layer is going to deposit?
Sir, just you told us.
Mm,
There is no
see, perlite
no
will
any addition
contain
or something.
addition alternate layers of alpha phase and
And
Fe3C. Okay,
yes, yes.
alternately. So something like this. Okay, this is like this. Okay, so this is what is perlite. So alpha and Fe3C. So in the hypereutectoid, so this is which region is hypereutectoid and which region is hypoeutectoid?
सर 0.8 के बाद हाइपर इटेक्टॉइड और 0.8 से पहले हाइपो.
Yes. So this is hypereutectoid and this is hypoeutectoid. So in hypoeutectoid, we will have perlite plus Fe3C. That is cementite. Fe3C is basically cementite. So the correct option is option number C. Now the next question: austenite transforms to bainite only during which of this process?
सर आई थिंक ऑप्शन ए, क्वेंचिंग.
Quenching is the process in which austenite will transform to martensite. Okay. So see, if we see the cooling diagram, say let us draw the TTT diagram. First tell me what is TTT. Can anybody tell me what is TTT?
सर टेम्परेचर ट्रांसफॉर्मेशन डायग्राम.
Then what is the third T? You gave me only two T's. This is the
सर
temperature.
टाइम.
Yes,
टाइम.
yes. This is time. So temperature time transformation diagram. So this is also called a controlled cooling. Okay, that is the cooling will be maintained at a fixed temperature. That is isothermal cooling mostly. So in this case, if we draw this, there will be something like this. Okay, say this is 800 degrees and above 800 we will only have homogeneous austenite. This is called, what is this called? Okay, we will come to it later. So this is the perlite coarse. If we reach this region, we will get coarse perlite. This is fine perlite. This is bainite, called upper bainite, which is actually coarse. And then this is bainite, lower bainite. Okay, now say this is around 400. This is the martensitic start temperature. Now If we have a cooling like this, what will we get? It is already denoted. You can tell me, right? What will we get in this case as a final product? Yeah. See, it is already denoted at per course per light. Okay. If there is quenching like this, say, this will be quenching. Then we will get martensite. This process is called quenching. Okay. What is called mar tempering? So mar tempering will be the process wherein we will reach the martensite and then we will hold it with this temperature, at this temperature. This is called mar tempering. Spheroidizing, we know that spherical layers of cementite are formed in a perlite matrix. And what is, so we are left with os forming. What happens in os forming? In os forming, we bring it like this and then we keep it like this at this temperature. So bainite is formed. Only bainite will be formed in os forming. Okay, bainite. So you can now ask me which of these terms is not clear to you. See, if you do not ask, I will by default have to take
Clear,
that you
so
have
clear.
understood. I don't understand. Like things are becoming clear, but like some of the things you are not able to answer. I would like if you interact during the like even during the explaining, when I am explaining, if you interrupt and ask, it will be very good for you to understand more. Anyway, so for os forming, austenite will transform to bainite during the os forming process. Okay, so the correct option is option number C. Annealing of carbon steels helps to which of these? So in annealing process, what do we do? In annealing process, here can you tell me uh, which are the upper critical temperatures and which are the lower critical temperatures in this diagram? See, these two are the upper critical temperatures, these two lines, and this is the lower critical temperature line. In annealing, heating is done 50 degrees above the upper critical temperature value, okay, and it is held at that point.
सर आयरन कार्बन डायग्राम में एक बार और बता दो, अपर क्रिटिकल टेम्परेचर, लोअर क्रिटिकल टेम्परेचर।
ये this one is the upper critical temperature, this one and this one, इनके बीच में जो है, जो गामा प्लस अल्फा रीजन और गामा प्लस Fe3 रीजन, that is called the intercritical temperature, and this is the lower critical temperature below this. मतलब जहां से ट्रांसफॉर्मेशन चालू होगा, if we heat from this region, then from this point the alpha and perlite will start converting to gamma plus alpha. Once we reach above the upper critical temperature, only austenite, that is gamma, will be present. So that is what is the upper critical temperature and the lower critical temperature.
ओके सर।
So heated and to 50 degrees above the upper critical temperature, matlab somewhere here it is heated, somewhere here, and it is held, so that to decrease the hardness and increase ductility. So see, increase hardness, so this is it is done to decrease hardness, so this is wrong. Decrease ductility, it is done to increase the ductility. So decrease in the hardness and increase in the ductility will result in the decrease of the residual stresses, because since the ductility is decreasing, so that means you can say that the brittleness, ductility is increasing, that means the brittleness is decreasing. So all the residual stresses that might have been there, the compressive or the tensile residual stresses, because it could not deform properly because of the limited ductility, those will be relieved. So decreasing residual stresses. So annealing is done so that to decrease the hardness is 1, to increase the ductility is 1, and to decrease the residual stresses. So from the options given, the correct option will be this one, relieving residual stress. Now coming to the next problem, short blasting of the metallic surface improves which of these? See, short blasting is a kind of strain hardening process wherein we have explained it much previously. Also, we have explained it many a times that what does strain hardening do? So, short blasting is where you repeatedly blast the surface of a material or surface of a substrate with either steel balls or sand particles or stuff like that, so that there is some plastic deformation and does strain hardening on the surface. So what does strain hardening do? So by now you know, right, what does strain hardening do?
सर ऑप्शन ए।
Think again, how will it improve the surface finish?
I think so, sir. B, fatigue strength.
Why B?
So this bombarding, no,
Yes,
bombarding on the surface.
yes.
So that's fatigue strength should have to
Yeah,
withstand for
so
that.
what happens is that I am asking you why hardening. So there is strain hardening. So strain hardening will induce compressive. We have said that strain hardening results in the increase in the yield strength, or there is in compressive residual stresses induced in the material. Compressive residual stresses. Okay, so because of the compressive residual stresses induced in the surface, under fatigue loading, what happens that there will be repeated tensile and compressive loadings. So repeated, if there is repeated tensile and compressive loading, the induced compressive residual stress will prevent the cracking due to this, when there is tension, when there is tensile stress. So or if there is no compressive stress, even if only tensile stress is applied repeatedly, in that case the induced compressive residual stress will improve the fatigue strength by like acting opposite to the applied tensile stress. So it improves fatigue strength. Option number B is the correct answer. Now coming to the next question. According to the Hall patch relationship, the yield strength of the metal is directly proportional to or directly or inversely proportional to which of these? So do you know what the Hall patch relationship is? See, we have told this numerous times or discussed this numerous times that finer grains results in increased hardness or decrease hardness, or the strength. Suppose this is the grains.
Increase.
Yeah. So the strength. So the strength will be more for which one? Fine or coarse?
Fine, sir.
Yes. And this is lower yield strength. Why is the yield strength more for fine? What is the main reason? As there are more dislocations,
Yes, sir. Yes, sir.
or you can say that the dislocations are more dislocations. So now you relate this yield strength with the diameter. Where is the diameter more? Relate the yield strength with the diameter. So where is the diameter more of the grain or the size of the grain?
Serene course.
Yeah. So as the as the diameter is increasing, the yield strength is increasing or decreasing?
Decreasing.
Decreasing. So yield strength is inversely proportional to the diameter of the grain. Okay. So this is what is the Hall patch relationship. Okay. So the correct option is inversely proportional to the grain size diameter. That is B. Okay. Now coming to the next question. Cold cracking in fusion welding process of hardenable steel is promoted by which of these? Cold cracking, sorry about that. Cold cracking refers to the cracking that happens after the solidification has already occurred. So if the material is ductile, will it result in cracking or it will oppose cracking?
It's opposite cracking, sir.
Yes. So opposes cracking. Now martensitic transformation. So what is martensite? Is it hard or soft?
Sorry, sir, I don't know.
So martensite is basically very hard, like extremely hard. The hardest that can be obtained in this case, like by the transformation. So martensite is hard. So a hard material will oppose cracking or it will support cracking.
It's support cracking, sir.
Yes, support cracking. And if absence, there is no hydrogen or inclusion in the weld, then it will support cracking or oppose cracking.
Oppose cracking.
Yes, oppose cracking. So the cold cracking will be promoted, that is supported by only one, that is the martensitic transformation, right? Because it is a hard phase, so the cracking will be easier. So cold cracking is promoted by B martensitic transformation. So is it clear to everybody?
Yes, sir.
Yes, sir.
Okay. Now strength of the butt brace joint can be increased by which of these? You know about bracing, right? What is bracing? What happens in bracing?
Strength is going to be increased, or joint is going to be uh, mm, good. We can say that.
Like, is brazing same as any other welding process?
Little bit similar to soldering.
Yeah, it is little bit similar to soldering, but then what happens in soldering? Okay, let us leave brazing. What happens in soldering? Like,
Soldering. A filler metal is going to be come in a liquid stage, and that metal is going to be held the other material.
yes. So what happens is that there are two base material pieces, say like this, and then one filler material is placed in between. Okay,
Yeah,
so this is heated, and this will bond with the two pieces.
two
Since
pieces. Yes,
this is mostly used if the two base metals, they themselves at low temperature cannot be fused properly, or if the materials are different. See, say suppose one is aluminum and one is, say, iron. So iron and aluminum, they have wide variety range of they differ in their melting points by like around 800 degrees. So in that case, it will be difficult that one will be too melted, one will be less melted, and like that. So in that case, if we place another material in between so that it can fuse with both the materials properly, then the then the joint can be placed. So in soldering, we use something called, so it mainly happens at less than the main difference is it happens at less than 427 degrees Celsius. We use something called solder, which is a lead and tin alloy as a filler material, which is called solder. In brazing, it happens above 427 degrees Celsius, and the filler metal that we use is called spelter, and it is an alloy of copper, mostly copper zinc, or say copper aluminum, or copper silver. Okay. Now, in this case, so in brazing, to improve the, see, this is this much of area. If we have, if we increase the surface area, then more amount of area will be in contact of both the base metal pieces will be in contact with the filler material, right? So that will increase the strength of the joint. Say supposedly in this joint itself, we are making a section like this, and here we are making the base material, then more area will be in contact, so the joint will be stronger. So the strength of a butt brace joint can be increased by actually increasing the surface area. Say supposedly there is a joining of these two. If we use some pieces like this and pieces like this, then the area is increasing, right? So that is how the strength of the joint can be increased. So the strength of the butt brace joint can be increased by increasing the joint area. Okay, is it clear to you?
Yes, sir.
Okay. So the correct option, strength,
Is B.
uh, yeah, of butt brace joint can be increased by B, increasing joint area. Now, coming to the next problem, weldability of the material will be high if it has which of these properties? First, can you tell me what is weldability? What does weldability mean in like one sentence?
Is prone to weld.
Sorry?
Is prone to weld.
Yeah, so the ease of welding, you can say. Ease of
Ease of welding. Ease of weld. Ease of
yes.
welding.
So now, so which of these thermal expansion and low, melting temperature, which values of these will be facilitating the welding process?
Is it B?
Mm, a thermal expansion coefficient, if it is higher, then during the contraction, won't more residual stresses be produced?
Yeah, yeah. No, no, no. Yeah, yeah.
Then what should be the thermal expansion coefficient?
Should be the low.
Yes, so it should be low. Thermal expansion coefficient. And what about the melting temperature?
If it's low, then temperature is also low.
Yeah. So yeah, obviously. So if the melting temperature is low, then that means that lesser heat is to be supplied. Then it is easier for the person, right, to weld the
Yes, sir.
material. So the correct option will be option number C.
C.
Yeah. Now, coming to the next question, increase in the thermal conductivity and thermal diffusivity causes the weldability to what? So, now tell me, like ease of welding, how will it be influenced by thermal conductivity? So, for better welding, the thermal conductivity should be high or low.
Low.
Why should the thermal conductivity be low?
It's easy to weld, sir. If we, uh,
How is it?
it's
That is what
melt
I'm
it is
asking. Yeah. So what happens is that you the way to think is more like that if the thermal conductivity is low, then whatever heat is supplied, a lesser fraction of heat will be conducted to the base material and more heat will be concentrated at the point that we are supplying. That is why the melting will be easier and the melting and that is with lesser heat the melting can be achieved. So the thermal
yeah,
conductivity should be
high.
so the increase in the thermal conductivity will or wait weldability with increase in thermal conductivity So weldability decreases, right? Is it clear why?
No, sir. Please explain.
So see, just now you said right that if the to facilitate the welding process, the thermal conductivity should be low or high. Yeah, we just said right that the if the thermal conductivity is low, then the heat will be concentrated at the region that we are applying, and less will be conducted. So
Yes, sir.
the
Yes, sir.
welding
Yes,
will
sir.
be easier. So if the thermal conductivity is increasing, then the welding will be difficult or easier.
Uh, is it difficult?
Yeah, because as the thermal conductivity increases, more heat will now be conducted and less heat will be
Take it.
concentrated at the region
Yes,
that
sir.
we are supplying. So the weldability will decrease in this case.
Decrease.
Similar for
Yeah.
say thermal diffusivity is what? K alpha, that is K by rho Cp, right? So thermal diffusivity, increase in thermal diffusivity means increase in thermal conductivity or decrease in rho Cp. So increase in thermal conductivity will again result in weldability to decrease, or decrease in rho Cp, that is less heat can be stored. Okay, rho Cp implies the heat fraction of heat that is being stored. So if less heat is being stored in the region that we are applying, then the uh, uh, um, melting of that region will be difficult. As such, the weldability will decrease. So for both of these reasons will cause the weldability to decrease. So with the increase in thermal conductivity and thermal diffusivity, the weldability will decrease. So that is decrease for both.
Yes, sir. Yes, sir.
Now coming to the next problem. Mm, yeah. So in iron carbon alloys, as the carbon content increases, which of these happens?
A.
Hardness increases and the tensile strength decreases. Okay. So it is not necessarily that the hardness increases is correct, but the tensile strength will actually first increase and then decrease. So if we draw the iron carbide diagram, okay, we'll get something like this. So this is the say region of eutectoid point, that is 0.8. Okay, and this is just a simplified diagram of. Now if we see the hardness, okay, then the hardness will increase like this. The tensile strength, however, will increase till this point and then decrease.
Then it's going to decrease. Yes.
Okay, and the
So
ductility,
here will be the B. Huh.
and the toughness both will continuously decrease.
Yeah. Right, right. So answer will be B, sir. Then.
Hmm. Or tough. Okay. So the correct answer is option number B.
Yeah.
Now coming to the next question. So for what value of carbon equivalent is welding not recommended? So what is carbon equivalent? See, for low alloy steels, that is for any steel, the carbon equivalent will give a number which is equal to the carbon content plus the other alloying the some particular fractions of the mm, other alloying elements. Say, suppose silicon is present, then whatever weight of silicon is present in the steel, we will take 25% of that. Say manganese is present, then we will take 6% of the fraction of the manganese that is present. So in that way we will get a number that is called a carbon equivalent. So since all these additives, that is manganese or silicon or whatever it is, they all these additives will tend to increase the hardness and decrease the ductility. So with greater hardness comes the problem of welding, because the cracks will be easily formed. That is why, so up to only a certain number of carbon equivalent, that is a certain value of that number, the welding is recommended, and after that the welding is not recommended. Okay, so that is the carbon equivalent. And the carbon equivalent range is such that if the carbon equivalent is less than 0.4, then it is easily weldable. If the carbon equivalent is between 0.4 and 0.7, then weldable with heat treatment, that it either has to be annealed or preheated. Okay, you can say. And if the carbon equivalent is greater than 0.7, then it is welding is not recommended. Okay, so the correct option is option number D, that above
Yeah.
0.7, if the carbon equivalent is above 0.7, then the welding is not recommended. So is it clear to
Yes.
you?
Yes, sir. Yes, sir.
Okay, so the next question, in heat treatment, the soaking is done for which of these? So can you tell me what is soaking? So what is soaking? So suppose this is homogeneous austenite region. After we get only austenite. Okay, so for anywhere you start heating, so it reaches this point. This is called the heating region. Now you keep to make the region completely homogenized, we will have this soaking time. Okay, and then it will be either quenched, it can be quenching, it can be annealing, or it can be normalizing, or whatever. So why is this mm, uh, soaking done? To make the austenite homogeneous. We can draw this in the form of a chart where okay, and this is this and this is the time. Okay, this is time and this is the temperature. Say this is the soaking temperature. Okay, soaking temperature. Now, at wait, before we start, say it had alpha plus perlite. We are starting from this region, say alpha plus perlite region. alpha plus perlite plus some other this whatever silicon whatever that vanadium or manganese or whatever is present, the carbides of that. So C means carbides. Okay, so as we heat it, okay, up to say this temperature, this is heated. First the mm, mm, alpha and carbides will remain the same, but the perlite will convert to austenite. Okay, next the carbide will remain the same and alpha ferrite will convert to austenite. Next, because of these carbides, there will be, like, carbides are essentially alloying elements, some different alloying elements, right? Say manganese or silicon, whatever their carbides are there. So they are non-homogeneously distributed. So that will result, further heating will further keeping it in the soaking time will result in homogeneous austenite. And then if we keep it further, then only homogeneous austenite is formed, and homogeneous austenite is the only uh, 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 form from which we can start the cooling process, whatever be it, quenching, normalizing or annealing, so that from that homogeneous state we can get the grains. So that is why the soaking is done. Okay, so the soaking is done to make the austenite homogeneous. So the correct option is
Is C.
C. So our main aim is to make this homogeneous.
No, homogeneous.
Answer is option number C. Okay, so yeah, so let us end for today. We will
Thank you,
continue
sir.
with
Thank you
this
very much.
in the next class. So that will essentially be the last class. So I request everybody to attend. Okay, thank you. Thank you for
Yeah.
joining.
So can you give the exam pattern?
The exam pattern, I think so. There recently a mail has been triggered to everybody regarding
Uh-huh.
the form in which the exam will be taken. Okay, the exam pattern uh, is not actually in our hand, so it will be done by the host institute. So if there is any doubt you have regarding this, then it's better that you talk directly with the TAs or the professor of the host institute, that is IIT Roorkee.
Okay.
Okay, so because
Okay.
they will be
Okay.
setting the question papers and the entire thing will be in their hands, so it's better that
Okay.
you get the information from them.
Yes. Yes.
Okay,
Thank you, sir.
thank you.
Thank you, sir. Thank you.
Yeah,
Thank
yeah,
you.
thank you.
Good night, sir. Good night. Good night. Good night.